Welcome, this is lecture 47. We want to continue looking at this maximal homogeneous subideal. So recall, okay, I is, this is Z graded, and for I inside that, define I star to be the maximal homogeneous ideal of R inside I. Okay. And we saw that if P, we saw last time that P prime ideal implies that P star is also a prime ideal. Okay. So now we want to make two observations, lemma, write them. Okay. Let R be a graded ring, Z graded as, and P a prime ideal. Okay. If P is not homogeneous, then height of P mod P star is 1. Then P won't be equal to P star, and but there can't be any ideal, homogeneous or not, any ideal strictly between them. Okay, so height of this is 1. Proof. Okay, so of course this is a statement about chains going from P star to P. So we may as well just kill P star, and which is a prime ideal. So we may as well kill P star and then look at chains going from 0. So going modulo P star, we may assume that P star is 0. Okay, so P is a homogeneous and that R is a domain. P star is a prime ideal. This we established last time. Okay. So now we think, if you think about this, we have a prime ideal P which does not contain any homogeneous ideal. So that's what P is a prime ideal that does not contain any homogeneous element, non-zero homogeneous element, does not contain any non-zero homogeneous element. Okay. So if we invert all the non-zero homogeneous elements, P would still be a prime ideal there, and more importantly, any chain between 0 and P will be preserved there of the same length. Okay. So note that the set of non-zero homogeneous elements is multiplicatively closed. Okay. So this is a okay, if you have two homogeneous elements, their product is homogeneous and non-zero. We are working in a domain, so it's non-zero. So it's multiplicatively closed. Okay. Therefore, every chain of primes, okay, ending in P, okay, will be preserved in the sense, preserved in the sense that it will give a chain of the same length. Maybe will give a chain of primes of the same length in U inverse R. Sorry, what is U? Let's call this thing where U is that set, where U is the set of all non-zero homogeneous elements. Okay. So in the ring U0R, there are no, every homogeneous element is invertible. In U inverse R, so this is a, okay, U inverse R is graded. Okay, its decomposition is, it can be written, every element can be written uniquely as some homogeneous element over some element inside U which are also homogeneous. So this is graded, is a graded ring. It's a graded ring. Okay. So in particular, so what do we know? And every non-zero element, every non-zero homogeneous element of U inverse R is invertible, okay. Which means that U inverse R is a field, okay, or U inverse R is isomorphic to K adjoint T inverse, where K is a field and T is a variable. Okay, so this or this. But this is not possible because we know that the prime P gives a non-zero, non-trivial prime inside U inverse R. So this is not possible. Since P extended to U inverse R is a proper non-zero ideal. So U inverse R could not be a field. Okay, so this is not possible. Therefore, it is of this form. Okay, so and therefore, but this ring has only two kinds of primes. There is the zero prime ideal, and then there is all the maximal ideals, which is not T. Okay, so exercise. Okay, spec of K T inverse is spec of KT minus the maximal ideal generated by T, the set containing the maximal ideal generated by T. Okay. Every other maximal ideal, every other prime ideal of KT has its image here is a prime ideal, proper prime ideal, except for this is the case there. So which now implies that height of P U inverse R is 1. It is not 0, therefore it can only be 1, which now implies that height of P is 1. Okay, it could not have been bigger than 1. Okay, so this is the proof, which is what we wanted to prove. We reduced to the case where P star is non-zero, P star is 0. Then we wanted to show that P was height 1 prime. So this is what we needed. So this is where the lemma about the structure of such rings. Every non-zero element is was going to be used. Okay. Another lemma. Okay. If P is in the support of M, so M is graded now. M graded. So it means it's generated by homogeneous elements. Okay. Then if P is in the support of M, okay, then P star is in the support of M. Okay. So let's just assume for this case that it is finitely generated. Because the argument is okay. So the observation is that P is in the support of M if and only if. This is where the finitely generated is used. P contains the annihilator of M. Okay. But annihilator of M is the intersection of the annihilator, individual elements of a generating set. And we already observed that annihilators of homogeneous elements are homogeneous ideals. So intersection is also a homogeneous ideal. So this is a homogeneous ideal. Okay. But P contains a homogeneous ideal, and P star is a maximal homogeneous ideal containing inside P, and so therefore this is equivalent to saying P star contains annihilator of M, which is equivalent to saying that P star is in the support of M. Okay. For non-finitely generated modules, this first equivalence and third equivalence may not hold. That support of M could be very small, but annihilator could be 0. Okay. That is possible, but for finitely generated modules, this is true. Okay. Yeah. So now we come to a description of the support of a finitely generated module theorem. Okay. R Noetherian graded. Okay. Sorry. In this lemma also, in this proof I assumed R Noetherian. Let's anyway. We need to worry about this only in the Noetherian case. Graded M finitely generated graded module. Okay. Let P be in the support of M. Okay. We'll make 4 statements successively building up, and so 1. If P is a minimal prime of M, then P is homogeneous. Okay. This is really the previous lemma. If P is a minimal prime, then P star is also minimal prime, therefore P must be equal to P star. Okay. I mean, if P is a minimal prime, then P star also contains annihilator of M and is inside P, so P has to be equal to P star. Okay. So I'll write down, but this is just the previous lemma. 2. Let D be equal to dimension of M localized at P. Okay. So now we have lost all grading. It is just a local ring, and I mean, this is a so this, when we say this means as a module over RP. Okay. So over RP, MP is a finitely generated module, and it's just a Noetherian local ring and a finitely generated module over it. No sense of grading at this when we make this statement. Okay. If D is positive, okay, there exists a chain of primes, chain of homogeneous prime ideals, chain of graded prime ideals, P0 inside up to PD minus 1. So all of these are homogeneous ideals inside P. So sorry, just to clarify, these are the homogeneous ones, not P. P itself is not given to be homogeneous. Just to clarify, okay, we're not asserting anything about P. Now let's assume 3. If P is homogeneous, then dimension of the local ring, dimension of the module at over the local ring, this is dimension as an RP module, is determined by a chain of graded prime ideals. Okay, so in other words, if D is the dimension of this dimension, then then there is a chain of primes in which P is also homogeneous. Okay, so sorry, in this case we can assume strict inequality here also. Okay. So there if P is homogeneous, we can take this P also to be homogeneous. I mean, this is that same P. Okay. So then we get a chain of length D, and hence that determines the dimension. Okay. And for if P is not homogeneous, okay, dimension of M localized at P is dimension of M localized at P star plus 1. Okay. So proof, I'll prove 2. We'll leave, I'll leave 3 is immediate from 2. 4 requires a little bit of thought, but I will leave that as an exercise, so that one becomes familiar with this sort of calculation. Okay. So 1 is immediate from the previous lemma. Previous lemma said that anything, if P is in the support, P star is also in the support. Okay. So let P be minimal prime over M. Yeah, actually, let me write the proof using previous lemma. One could prove it slightly differently also, but we will do that. So let P be in the support of minimum of M. So this implies now that P star, so this is inside support. This is the minimal elements in support. P star is inside support of M. Okay. But by definition of minimality, this one says that P star is also in minimum elements of M, which the only way it is possible is P is P star. Okay. So another argument could be that minimal elements of this minimal elements over M, minimal primes over M are associated, but we had already observed a while ago that associated primes are homogeneous, because associated primes are annihilators of homogeneous elements. In this particular case, one can show that, and so this is homogeneous. 2. So 2 is the technical part. So I'll prove that, and the rest 3 is immediate, and 4 is I'll leave it as an exercise. So 2. So we induct on D. Okay. We assume that statement only for positive D. Okay. So if D is 1, okay, then we have P0, okay, P0, so there exists P0 inside min of M. By 1, P0 is homogeneous. Okay, and also since D is 1, P0 is properly inside P1 P. Okay, so therefore we got, if D is 1, we just need to find one prime homogeneous prime ideal that we can take as one in the minimal primes itself. Okay, so now assume D greater than 1 and assume it is true for smaller d. Okay. So then okay. So choose look at, so since dimension of M localized at P is D, there exists a chain of primes P0 inside P1 inside PD which is equal to P, because that's somehow the dimension has to come from a chain of primes. Okay, so this is true. Okay, let's look at PD minus 1. D is greater than 1, so we could, D minus 1 is still positive. Okay, so look at M localized at P d minus 1. Okay. So this one's dimension is less because it's inside one shorter chain of primes. Okay. So this by induction, look at this, whose dimension is less than d. Okay, so now we can use induction. Okay, so by induction, we can assume that the first d minus 2 of those, P0 through P d minus 2 are homogeneous. P0 through P d minus 2 are homogeneous. Okay, no, nothing about P d minus 1. Because in the theorem, there is nothing about PD, which is P. Sorry, maybe I forgot the, it is only about P0 through PD minus 1 that we are asserting, that there is homogeneous prime ideals. Last one, there is no assertion. Okay. So, same thing, we get, this is homogeneous. Okay. Okay. What about height of P over PD minus 2? Height of P mod PD minus 2, okay, it has to be 2 because if it is, well, it is at least 2 because there is a PD minus 1, probably not homogeneous, and then there is P, so it is at least 2, but it cannot be bigger than 2 because you have already covered d minus 2 elements, and if after this there is bigger chain longer than 2, then dimension would have been greater than d. But since dimension is d, this is equal to 2 itself. Okay, so let me just say this again. It is at least 2 because after this, after this there is a, after this there is a P d minus 1, which is there because, okay, and then there is P, okay, so there is at least 2. So this, therefore this is at least 2. So this gives this. So this gives at least, and then we observe that if there is more, there is a longer chain, okay, then dimension of M localized at P would be bigger than D, but we said D is the dimension, so that says it is less than, and together it's equal. Okay. So dimension of this is 2. This implies that P star must properly contain PD minus 2 because P mod P star has height only 1, but P mod PD minus 2 has at least 2, and PD minus 2 is homogeneous. Okay. So it is possible that P is homogeneous. Okay, so we are not asserting that P is not equal to P star, but in either case, P star cannot be equal to PD minus 2 because the difference in height is 2, not 1. Okay. Now let R be inside P star, but not in P, not in PD minus 2. Okay, and let P d minus 1 be minimal over over P d minus 2 plus R, okay, such that P d minus 1 is inside PD, is inside P. So this is a homogeneous ideal. A minimal prime will be homogeneous, and we choose a minimal prime inside this. Or let's argue, we don't need to worry about homogeneity now. This prime, this is some ideal inside P. Height of P d minus 2, height of P over P d minus 2 is at least 2, is equal to 2. So there must be a prime which contains this bigger ideal and P. There must be a prime ideal containing those two. Among them, take one that is minimal, that would be homogeneous, and therefore we have got P d minus 2, P d minus 1 also, and this is the Okay, so this is so PD minus 1 is homogeneous because it is minimal over homogeneous prime ideal, homogeneous ideal. This R has to be taken to be homogeneous. Okay, so this ideal is homogeneous, therefore a minimal prime is also homogeneous, and that is the end of the proof. Okay, so this is 2, and 3 and 4 I leave as an exercise. 3 is immediate, 4 requires a little bit of thought. If P is not homogeneous, then the dimension is smaller because P star, there are any chain from up to P star in the support of M can be extended by at least 1, but it cannot be smaller by more than 1. Okay, so just think a little bit, and one can prove this. So these are exercises. Follows from 2 really. Okay, so this is the general structure of graded rings, Z-graded Noetherian rings, and finitely generated module over them. How chains of primes will look. So therefore, when we want to look at graded rings, now we will restrict ourselves to polynomial rings in one variable, in finitely many variables over a field. And when we want to look at them, we will worry about graded ideals. Okay, and there are applications to. So hereafter we will worry about these things. So in the first lecture, maybe a little bit of in the next lecture, and a little bit after that, we will discuss some one thing called the Hilbert series of a graded module. It builds on what we did earlier about Hilbert polynomial and Hilbert function and Hilbert polynomial. It's just another way of representing the same data, has certain advantages. So we will learn that. Then we will sort of worry about applications of these graded concepts in geometry, and we will also look at some things. Tie these things back with Grosvenor basis. Okay, so that will be the content in the next few lectures.